If you are wondering what am I doing with an 84 kilowatt Tesla turbine and why am I connecting the exhaust of the Tesla turbine to a 12 kilowatt cryo chiller, and why did I install the cryo chiller's compressor into a barrel of water, and why did I connect the barrel of water to the cold side of an 11 kilowatt heat pump, why is the heat pump connected to a 150 liter domestic hot water cylinder, and why is the hot water cylinder connected to a big heat exchanger on the inlet fluid of the Tesla turbine. I'm going to give you a quick deep dive of what I'm doing with this Tesla turbine and why I've connected all these different things to it on the inlet and the outlet, and why I'm using refrigeration to run the Tesla turbine. So let's get into it. I am building an organic Rankine cycle generator. Now, before I can go on and tell you why I built this Tesla turbine, I need to explain what an organic Rankine cycle generator is. Normally, in a Rankine cycle generator, you would pump cold water up to pressure, superheat the high pressure water to steam, and then use that superheated high pressure steam to run a turbine which generates electricity, and then the water will condense and turn back into liquid and the cycle will repeat. In an organic Rankine cycle generator, we don't use water, we use an organic fluid like butane or propane because it has a much colder boiling point. Now, propane has a boiling point of minus 40 degrees Celsius at ambient pressure, and butane has a boiling point of minus 20 degrees Celsius at ambient pressure. We're probably going to start with butane and run the turbine on butane. And the reason why we have a cryo chiller connected to the exhaust is because we want to liquefy the exhaust before it goes to the ORC pump. The ORC pump that I'm using is a Hydrocell D10, which can pump anything. It is a 100% leak-proof pump, so the fluid cannot leak out while it's pumping. It doesn't have a shaft seal issue, and it can pump minus 40 degrees Celsius up to a maximum of 103 bar, which is insane. The pump is also running on this giant 1 kilowatt motor, which is a 3-phase induction motor, which is very efficient. And it's running on a variable speed drive or a variable frequency drive, so that we can control how fast it goes and how much volume it pumps and how much pressure it pumps, so that we can control the flow rate so that we don't suck in bubbles. The heat pump that I'm using is a 5 kilowatt heat pump compressor that's been built into an 11 kilowatt heat pump shell. And the 11 kilowatt heat pump compressor has been built into the cryo chiller, which is running underwater at the moment. The coldest part of the cold side of the heat pump is going through the barrel of water to actually cool down the water to hopefully less than 0 degrees Celsius. The cryo chiller's compressor can run colder than 0 degrees Celsius while it is trying to cool down the refrigerant of the cryo chiller. So when you look at an air conditioner's rating, you'll see that a 3 kilowatt air conditioner has a 3 kilowatt cooling capacity. But when you run it as a heater, it has a 4.7 kilowatt heating capacity. Because when you run an air conditioner for cooling, then it fights its own thermodynamic loss, which makes it a lot more inefficient. And when you run that air conditioner as a heater, it consumes its its thermodynamic loss as an advantage. When you are trying to cool down a situation like with a fridge or an air conditioner or a freezer, then the hot compressor will cause the incoming low pressure gas to expand, to heat up and to expand before it gets compressed, which is a massive thermodynamic loss. The slightly warm refrigerant to go into a cold compressor so that either doesn't expand or it shrinks before it gets compressed, which will make it a lot more efficient. The heat pump has a cold side, and that cold side belongs to us. So we want to use that cold side before it goes to pick up heat energy from the atmosphere, so that our cryo chiller can run a lot more efficient, either cool down a lot more or it will use less electricity. The heat pump is going to run on R32 refrigerant. The ORC pump is going to run on butane. Then we'll go to a butane and propane mix. And if that works very well, we'll go to propane. Depending on what happens after that, we will probably change to a refrigerant or a mixture of refrigerant that is more efficient. The alternators of the generator are housed inside of these exhaust tubes. The power then goes through a bridge rectifier, which will then come out at about 54 volts DC, which will then send through a maximum power point tracker that is built into an inverter. The inverter will then output power, which we will measure, and eventually we will reuse it in the system. And if we're lucky, we'll have excess power over how much we are using to run the system in the first place. So we're just going to get it started. And once I got it started and it is working, even if it is working badly, then I will tweak up here. And I will tweak the system as well so that I can find that efficiency sweet spot where we can harvest heat energy from the atmosphere as a renewable energy source. But it would be a non-intermittent renewable energy source. So if I get it right, the technology can then be used as a non-intermittent renewable energy source, but it could also be used as base load. And if we tune the sweet spots of the refrigeration in the different parts very well, then it will produce water as a byproduct. If you've made it this far, then please subscribe and like the video, and I'll see you in the next one.